Good morning and welcome to the lecture number 38 of the course Water Resource Systems, Modeling Techniques and Analysis. Now, in the last lecture, we checked the modeling technique for conjunctive use of surface and groundwater. We considered a simple model where we look at the continuity at the surface reservoir and the continuity at the groundwater reservoir and see how the two are linked. We introduce certain linking constraints through the seepage that takes place as the water flows in the canal and contributes to the groundwater storage, and the pumping that we do from the groundwater subsequently also part of it comes and recharges the groundwater. So, we considered the recharge to the groundwater. We specifically looked at this particular type of system where you have a surface reservoir fed by the inflow due to the catchment rainfall. There is a evaporation that is taking place, then the canal release, which is the decision variable. The part of the canal release contributes to the groundwater as canal recharge, and then the water that is applied both from the surface as well as from the groundwater source. Part of it also comes as deep percolation and then may contribute to the groundwater aquifer. The decisions that we are making in this particular problem is the rate of pumping as well as the amount of release that needs to be made from the reservoir during different time periods within a year, and typically we consider monthly time periods, 10-day time periods and so on. And we also solved an example, simple example actually, where we considered lumped storage continuity here, lumped storage continuity at the aquifer. I mentioned towards the end of the last lecture that you can make the groundwater model as sophisticated as you desire by including, let us say, the two-dimensional groundwater flow equations and then dividing this aquifer into a number of elements, and you use finite element method to solve the differential equations. When you do that, you must write these balance equations corresponding to each of the element. Let us say that you are discretizing the irrigated area into a 2 kilometer by 2 kilometer grid, and you write the finite element model in 2 kilometer by 2 kilometer for the aquifer, and then for every 2 kilometer by 2 kilometer grid you need to write the balance equations. Such studies are available in literature. Those who are interested can go through that. Now, we will look at another important problem where we will formulate an optimization model for hydropower generation. In our earlier lectures, somewhere around lecture number 25, 26, we have seen the simulation for hydropower, where we have seen the relationship between the power that is produced at the powerhouse with the head available in the reservoir and the amount of release that you are going to make through the turbines. It is a nonlinear relationship typically given by power being proportional to QT into HT, where QT is the discharge through the turbines and HT is the net head available. Now, we will go one step further and then look at how do we optimize the power that is generated. And typically in most of the power generating projects, especially in countries like ours, we also have irrigation. So, power is in general a secondary objective and irrigation is the primary objective in most of the systems that we have in our country. In such a situation, we would like to optimize the hydropower generated subject to the irrigation demands being either completely met or irrigation demands being met with a certain minimum reliability and so on. So, we have two major objectives in most of the systems that we have in our country, irrigation and hydropower, where irrigation takes a higher priority in general. The problem that we pose now is what is the maximum power that you can generate for a given reliability of meeting the irrigation demands. So, we pre-specify the reliability of meeting the irrigation demands, and then for that pre-specified minimum reliability of meeting the irrigation demands, we look at what is the maximum power that we can generate from a system. So, we will formulate a problem of such a type and then see how we interpret the results, how we look at the trade off between the reliability of the power with respect to the reliability of the meeting the irrigation demands and so on. So, there will be a trade off between hydropower reliability and the irrigation reliability, and that is what we will examine today. So, we will take a system, a typical system in fact, which exists in most water resource systems in our country, where you have a surface reservoir and then you are letting out water for irrigation through the canals, and you may have a small amount of power generated through the canal bed powerhouse. So, CBPH that I have shown here is a canal bed powerhouse. So, it may be a very minor amount of power that is generated through the water that is let out in the canal for irrigation. However, you may have a river bed powerhouse, and this is the powerhouse that generates major power at the system at the reservoir, and release has to be made specifically for RBPH, that is the riverbed powerhouse, in addition to the release that is made already for irrigated area. Now, this is a type of system that we will consider now. We will look at the maximum power that can be generated through the riverbed powerhouse for a pre-specified reliability of meeting the irrigated demands during different time periods in the year. Now, this will be constrained, both of these will be constrained by the supply that is available, which is determined by the flows, inflows to the reservoir, and they are generated because of the rainfall in the catchment area. Now, this is a typical problem that we will look at. I again repeat that we will not optimize the CBPH power, that is the canal bed powerhouse, because we are simply saying we are going to meet the irrigated irrigation demand with a certain level of reliability, and therefore, that release gets fixed or that release gets determined based on the irrigation demands and the pre-specified reliability. However, we will optimize the power that is generated through the riverbed powerhouse, and riverbed powerhouse generally will have much larger capacity compared to the canal bed powerhouse. Now, when we are looking at such a problem, we will as I said, we may say that we want to meet the irrigation demands 100% of the time. Then what is the power that is generated? We may want to meet the irrigation demands at least 90% of the time. Then what is the maximum power that we can generate all through the year, subject to the uncertainties associated with the inflows. Then we may want to look at the irrigation demands to be met with a certain reliability, let us say P. P is the probability of meeting the irrigation demands, which means the minimum probability, which is also the reliability of meeting the demand. And then we start looking at various levels of power that is generated and the associated reliabilities. So, these kind of trade offs that we can generate, that means the reliability of meeting the demands with respect to the reliability of the maximum power that we can generate here and so on. So, we will formulate first a chance constrained reservoir optimization problem for this, in which we will pre-specify the reliability of meeting the demand and then look at what is the maximum power that we can produce. Now, that is what is stated here. So, we want to maximize the hydropower production subject to satisfying irrigation demands at a specified reliability level. Now, water drawn into irrigation canals also produces small amount of power, but we will not consider this in the optimization. But the main power that is produced out of the water that is released downstream of the reservoir into the riverbed powerhouse itself. And in the process, because the inflows are random, the flow into the irrigated area. Now, we are putting this as a reliability criterion. So, we are saying that the demands to be met with a certain reliability. This is a pre-specified reliability. And because of which the release here, that we will call it as IRT. Let us say that it is a irrigation release or release for irrigation. Now, this becomes random because it is dependent on the reliability here we are specifying, and that reliability will be achieved by the flow that is available or the supply that is available, and therefore, this becomes random. Theoretically or actually speaking, the release that we are making into the riverbed powerhouse is also a random variable, because it also depends on the storage, and storage is a function of the flows. By using the linear decision rule in a imaginative way, what we will do is we will convert the storage into a deterministic variable. Although the inflow is a stochastic variable, we convert the storage into a deterministic variable, thereby converting the release into the powerhouse, riverbed powerhouse, as a deterministic variable, whereas the release into the canal here, irrigation canal, that becomes a random variable. So, we will formulate a chance constraint program to maximize the power produced in the riverbed powerhouse, subject to certain pre-specified reliability of meeting the irrigation demands. That is the purpose now. So, we will write the chance constraint first. IRT is the irrigation release. Now, as I said, IRT depends on the supply that is available, and we are specifying that the irrigation demands must be met with a minimum reliability of P. Now, this is the probability of meeting the demand. Meeting irrigation demands, and this is the irrigation release that is made, and this is the demand in time period T. In general, we can also make this as PT. That means, we may specify different levels of probabilities for different time periods. So, this is the chance constraint now. We are going to make decisions on IRT. This is specified and this demand pattern is known. So, for every time period T, you know the irrigation demands. Now, this is a chance constraint, and we have the reservoir continuity ST, which is the storage at the beginning of the time period T, plus IT, which is the inflow during the time period T, minus IRT, which is the irrigation release, minus RT, which is the power release. So, for power release, I will put it as RT, and this is the evaporation. So, this is a simple storage continuity equation. We are not worrying too much about the evaporation being storage dependent loss. We will include that subsequently when we use the linear programming. So, right now for the continuity, you just understand it this way: ST, which is the storage at the beginning of the time period, you add the inflow, take out the irrigation release, this is irrigation release, take out the power release, take out the evaporation, then you will end up with storage at the end of the time period. This we have to write it for all T. Now, this continuity equation we will use to convert the chance constraint that we have written here into its deterministic equivalent. I suggest that you refer to the earlier lectures on chance constraint optimization. So, E t, as you can see here, E t depends on the average storage during the time period. Let us say that you are looking at the monthly at a monthly operation of the reservoir, and the E t, which is the evaporation loss in volume units during that particular month, will depend on the storage at the beginning of the time period and the storage at the end of the time period. So, we will write E t, typically it will depend on the surface area, that is a water spread area during time period t and time period t plus 1, and we are looking at the live storage here. So, we approximate the storage area relationship with a straight line, refer to the earlier lecture where we derived this expression, and then write E t, which is in the volume units, as a linear function of the storage at the beginning as well as at the end. So, simply write E t is equal to alpha t plus beta t into bracket S t plus S t plus 1. Now, S t plus S t plus 1 by 2 is the average storage. We may have area of water spread, or this is the slope of this line, and E t is the rate of evaporation. All of these are absorbed, and then we write E t in volume units as a simple linear equation, because we would like to use or formulate this problem as a chance constraint linear programming problem, and therefore, all the constraints have to be linear, all the relationships have to be linear. Then the evaporation loss, once we write this E t is equal to alpha t plus beta t S t plus S t plus 1, we put that into the continuity equation and write for I r t. From the continuity equation, I take the I r t into the left hand side, we get this as the continuity equation. So, we use this as continuity equation for irrigation release. Understand different terms here. Beta t comes from the evaporation loss equation relationship, and S t and S t plus 1 are decision variables, which are the storage at the beginning of the time period t and beginning of time period t plus 1. I t is random inflow. This is the inflow which is random, and R t is the power release, and again alpha t comes from evaporation equation. Now, alpha t is known, beta t is known, S t and S t plus 1 are decision variables, R t is a decision variable, I r t is a decision variable, I t is a random input. So, this is what you get here. Now, we had the chance constraint, probability of I r t greater than or equal to d t greater than or equal to p. In this, we have pre-specified the probability of meeting the demand. Let us say that we want to say 70% of the time the demands have to be met, 80% of the times the demands have to be met, there is a irrigation demand, and therefore, we may specify p to be 0.7, 0.8, 0.9 etc. So, these are pre-specified probability levels, and I write the chance constraint as I r t is given like this. I take I t to the right hand side. We are writing I r t greater than or equal to d t greater than or equal to p. This I write it as I t, I take it on the right hand side, and then rewrite this. I write probability of 1 plus beta t S t plus 1 minus 1 minus beta t S t plus R t plus alpha t plus d t, which was greater than or equal to d t was in the chance constraint there, and that would be less than or equal to I t, because I have retained this on the left right hand side, everything else I have transferred it to the left hand side, less than or equal to I t, greater than or equal to p. Now, this is the chance constraint in which I t is a random variable whose probability distribution is known. This probability distribution we determine based on the historical data that is available. Because I t is a random variable, S t that depends on I t becomes a random variable, R t becomes a random variable. However, what we will and therefore, it becomes complex. You cannot directly transfer the variance in I t to various different variables. So, what we will then do is, as we did indeed in our chance constrained linear programming explanation, we use a linear decision rule. We use the linear decision rule because we want to use a linear optimization. So, we use a linear decision rule. You just refer to lectures 29 and 30, where I have explained the linear decision rule. This is the irrigation release. So, the irrigation release we express as the total water that is available minus a decision parameter. So, S t plus I t minus R t, which is the power release, which we take it as deterministic, minus the evaporation, which we take it as deterministic, minus B t, where B t is a decision parameter. Now, remember here that R t and E t both are taken as deterministic. It means that whatever is the variance in I t or whatever is the uncertainty in I t is all transferred to the uncertainty in I r t, and R t and E t they are retained as deterministic variables. So, there is a subtle understanding that is necessary here, although because S t, R t, E t all of which depend on I t, which is the random inflow. What we are saying through this particular type of linear decision rule is that all the variance in I t or all the uncertainty in I t, we transfer it only to I r t, and S t, R t as well as E t, they are not uncertain, they become determinate, they are retained as deterministic variables. So, that is the understanding that you should have. Now, when we do this and convert the chance constraint as we wrote here into a deterministic equivalent, again you refer to these, you will get this as, first of all, using the continuity equation, you get S t plus 1 is equal to B t. The continuity equation is here, with evaporation it is written like this. With that, now you can verify that S t plus 1 will become equal to B t, that is for R t or for I r t you are putting this expression, and then you will get S t plus 1 is equal to B t. You go to your earlier lectures 29 and 30, you will be able to understand this. And therefore, effectively the storage is made deterministic. Remember, B t are the decision parameters which are deterministic. Because E t, which is the evaporation loss, and R t, which is the release that is made for power, both of them depend on storage alone, and storage is the deterministic variable. R t and E t also become deterministic. Now, that is the idea with which we use the linear decision rule. All right. Now, you look at this now, this is the chance constraint, 1 plus B t S t plus 1 minus 1 minus B t S t plus R t plus alpha t plus d t less than or equal to I t greater than or equal to p. P is the probability level, d t is known sequence, R t is deterministic, S t is deterministic, and therefore, the left hand side of this constraint is all fully deterministic, and the only random variable is on the right hand side here, I t, and this, the distribution of I t is known, probability distribution of I t is known, and this value is pre-specified. For this, now we write the deterministic equivalent. So, the deterministic equivalent turns out to be all of that left hand side of this expression, 1 plus beta t etcetera, and we are writing S t plus 1 is equal to B t. Therefore, S t will be B t minus 1 and all other terms less than or equal to I t, and that turns out to be, we write this as 1 plus beta t B t minus 1 minus beta t B t minus 1 plus R t, which is the deterministic variable, plus alpha t, which is a constant, plus d t, which is the deterministic known values, less than or equal to f I t inverse 1 minus p. Refer to lectures 29 and 30 and understand how we write the deterministic equivalents. You must know what is this term now, FIT inverse 1 minus P. FIT refers to the CDF, cumulative distribution function for the variable IT, and FIT inverse for a given value refers to the particular flow value IT. So, we are showing here the CDF of IT, CDF of the variable IT. For any given value of IT, the corresponding value is FIT IT. This IT, capital IT, says that it refers to the variable IT, and this small IT refers to the particular value of IT. And for a specified value 1 minus P, you go to the CDF, and the associated value on the x axis gives you FIT inverse 1 minus P. It is in fact the flow value corresponding to the CDF of 1 minus P, or the exceedance probability of P. So, FIT inverse 1 minus P is the reservoir inflow during period T with probability 1 minus P, that is CDF, corresponding to 1 minus P, or the exceedance probability of P, that is P percentage time that flow is exceeded, because f of x, remember f of x is probability of x being less than or equal to x. So, this is what you interpret from here. With the CDF x, we will say, not probability, we will say CDF of 1 minus P. So, corresponding to the CDF of 1 minus P, that is the inflow value. All right. So, we know from the distribution of IT, we know this value, because P is specified, you go to the distribution and get the FIT inverse 1 minus P. Now, all of this left hand side are deterministic, some of them are decision variables, some of them are constants, known constants, and so on. Then we put other constraints. One is the storage constraint itself. Remember, you have for the reservoir storage, you have a dead storage, and that dead storage is denoted as KT, and you have a total storage, and that is denoted as KT, K capital T, and BT minus 1 is nothing but ST. So, we are saying that the storage at any time period T must be greater than or equal to dead storage. We do not want to allow the storage to go down, and at the same time it should be within the total storage KT. So, these are the two constraints that we put for the storage capacity. Then we have the power plant capacity. If you have a power produced in time period T, we denote it as EBT. EBT is the total power that is produced in time period T, must be less than or equal to the plant capacity. So, this is plant capacity itself. Then we need to write EBT also in terms of the release and the storage. Now, we are writing all the constraints now. We will also write the objective function presently. Now, for writing ET here, EBT, which is the power produced, in fact, we are going to make decisions on the power produced. We want to maximize the power produced, and power produced is related to the head that is available in time period T, as well as the release RT that you are making to the turbines. So, first we will look at the head that is available. Now, HT, as I mentioned, if you are looking at monthly time periods, HT will depend on the storage at the beginning of the time period as well as storage at the end of the time period. So, we take the average of the storages and then look at the average net head that is available. So, we will write, if you recall, when I discussed the hydropower generation for simulation of hydropower generation, if you recall, we use the capacity elevation relationship. We want to determine the elevation for a given storage. By capacity, I mean the storage, and typically you will have a curve like this. This will give elevation capacity relationship. We use a linear approximation for this curve and write HT as a linear function of the storages. Remember, Bt minus 1 is nothing but St and Bt is nothing but St plus 1. So, we take St and St plus 1, come to this level, St plus 1 by 2 in fact, come to this level and then read the capacity. Now, that we are going to approximate by a linear relationship. We determine gamma and delta, which are the constants here, through the linear relationship or linearized approximation of the capacity elevation relationship. So, that for a given value of this storage, namely St plus 1 divided by 2, we will be able to get the Ht. Now, Ht is the total head and we may have a tailwater level. Recall that you have the dam here and then you have penstocks, the turbine is here and then you may have a tailwater level here. And if your level is here, tailwater level is here, this becomes the net head. This will be net head. And that is what we write as Ht as determined from here minus B tail, which is the tailwater level. Now, B tail is the tailwater level. So, that is how you determine the net head that is available for powerhouse power production. RT is the release that you are making through the penstocks to the turbine and Ht minus B tail is the net head that is available and therefore, you should be able to write the power that is generated. However, there is one more problem here, because you recall that the power that is generated is a non-linear function of the discharge and the head. Typically, we get power as proportional to Qt into Ht, where Qt is the release that is made into the penstocks and Ht is the net head that is available. So, what we do is we write now the product Qt into Ht as a linear relationship, and this I pick it up from Laux et al. 1981 and the reference is given here, you can refer to this. What we do is we write Qt Ht, where Qt is the release that is made into the penstock. In our case, it will be RT, I will just come to that, and Ht is the net head. So, we write Qt Ht is equal to Qt into Ht naught, which is known, and Qt naught into Ht, Qt naught is known, minus Qt naught into Ht naught, both of them are known. So, in this expression now, what I am saying is Qt into Ht, in which both of these are unknowns, we write it as Qt into Ht naught is known and therefore, some constant into Qt plus some constant into Ht minus this constant and this constant. That is how we write. Now, the question is, what are the values of Ht naught and Qt naught? I will come to that presently, but we will replace in our notation it would have been RT into Ht minus B tail. This is the net head and this RT is nothing but Qt, that is the release that is made. So, this is the expression that we need to express as a linear function. So, we will come to that. So, essentially what we are doing is multiplication of two decision variables, both of which are unknown, and multiplication of the two decision variables will render the problem to be non-linear, and therefore, to overcome that problem of non-linearity, we express the multiplication as Qt into Ht naught plus Qt naught into Ht, Qt naught is known, Ht naught is known, minus Qt naught into Ht naught. Therefore, this becomes a linear function. All right. Now, we are writing EBT, a slightly cumbersome notation, but just bear with me for that, because there are several repetition of variables and therefore, we need to be careful about the notation. So, we will say EB naught now. EBT is the actual power that is produced, and that will be dependent on RT into Ht minus B tail. Ht is unknown head which is dependent on the storage at the beginning of time period t as well as beginning of time period t plus 1. B tail is known, this is a feature of the powerhouse, therefore, the tail water level is known. This is unknown and therefore, this is a nonlinear function and there is a constant C here which will convert the net head and the discharge, the product of that into the power that is generated. So, the constant here is you can refer to our earlier lecture where we got something like this, P is equal to some number like this RT into HT which is the net head into the efficiency. So, efficiency into all of these can come into this constant here C. So, the constant C here is a constant to convert RT and HT into EBT, that is the power produced. That can be determined based on your specific case study. So, this we will write now as using this now expression Qt HT is equal to Qt HT naught plus Qt naught HT minus Qt naught HT naught. So, I will write this as C into RT into HT naught minus B tail, that is what I am doing here is I will retain only one of the decision variables in each of the terms, either RT or HT. So, RT first I will take the HT naught which is a constant head or which is a known head minus B tail is known plus RT naught into HT minus B tail. In this you will have only one decision variable HT, RT naught is given. In this you have only one decision variable RT, HT naught is given and the last term here is simply Qt naught into HT naught which is RT naught into this term here. Now, what we do is, so HT naught and RT naught are assumed constant here, because we are trying to convert a non-linear expression into a linear expression. And what we do is HT naught and RT naught we assume as the average net head, average head as well as the average release during the time period t. We solve, when we solve the model, I will write the complete model presently. When we solve the model, you will get certain values of RT as well as certain values of HT coming out as decision variables. Then you need to check whether this expression is in fact satisfied for the particular decision variables that we get out of the optimization. If it is not satisfied, you do it in a iterative manner. Let us say you got one value of RT and another value of HT and then the equation is not satisfied, the constraint is not satisfied. Then you set RT naught is equal to that value of RT and HT naught is equal to that value of HT as you obtained and then resolve the problem. So, this has to be done in a iterative manner. Alright. So, all these expressions are understood. So, EBT is a major variable which we are maximizing. This is the power now. We are writing this as the hydropower generated. We are looking at maximization of the hydropower. Then we also have constraints on the reservoir elevation for power generation. That means, you would like to operate the reservoir only within certain range of the heads, and that is what we specify as HT must be within this range between H min and H max, some minimum elevation and some maximum elevation, which need not be always corresponding to the dead storage and the total storage. So, this range is fixed by the turbine operation and you will know the values of H min and H max within which your head has to vary. Alright. So, all the constraints you understand correctly. We started with a chance constraint, probability of IRT being greater than or equal to DT, DT being the demands, irrigation demands, and this value, that is a probability value, must be greater than or equal to P, which is a pre-specified reliability level. We want to meet the irrigation demands with a minimum reliability of P, and P may be of the order of 0.8, 0.9 etc. So, 80% of the time minimum you need to meet the demands. Then you look at the evaporation. Evaporation depends on the area of water spread, and you are talking about a finite length of the time period, typically of the order of 1 month, and then you convert the evaporation into a linear relationship with respect to the storages by using the storage elevation relation, storage area relationship. Then you come to the head that governs the power generated. The head you express again as a linear function of the storage using the storage elevation relationship. Now, the storage elevation as well as storage area relationships are features of the particular reservoir, and these data will be available always. Then you look at the non-linear relationship R T into H T or R T into H T minus B tel in our notation, where you are talking about the product of the decision variable R T and the decision variable H T minus B tel. B tel is known, but H T is unknown, and that you express as a linear function of R T as well as H T by assuming certain R T naught and certain H T naught. And this model you solve again and again until R T naught and H T naught converge or they are such that the values, the expression is satisfied, the nonlinear expression is satisfied. That is the approximation of the nonlinear Q T into H T term or R T into H T minus B tel term is in fact satisfied. Now, we look at the objective function. The objective function here is that we are maximizing, the objective function is maximizing the total power that is generated in the year. So, we write this as maximize EBT, EB is one term, EBT, which is the power generated during time period T, and that we sum it over all the time periods within the year, and this becomes the objective function. So, we have the objective function, we have all the constraints ready with us. From the historical data, we know the CDF or the probability distribution of the inflows. We use that and then use the deterministic equivalent of the chance constraint and then formulate the linear programming problem. Use any linear programming software that is available. We use Lingo here. The Lingo software is readily available, and also it is very simple to use for large linear programming problems. You go to the Lingo software and then solve the problem. So, what we then do is that first we specify the value of P, that is, this is the reliability with which the irrigation demands have to be met. Then we assume values of H T naught and R T naught, and solve this problem, solve the problem because everything else is known now. Once H T naught and R T naught are assumed, everything else is known, or you can solve for those variables and then solve it. Then if the values of H T and R T in the solution are different from these, what I mean by that is that if your H T and R T are such that they do not satisfy this expression here corresponding to this, then we resolve that problem. Another run is made replacing H T naught and R T naught by H T and R T respectively. So, if your H T naught and R T naught are not very close to H T and R T, then you make another run by resetting H T and R T to be H T naught and R T naught respectively. So, the CCLP model we run successively until you converge. By converging, I mean R T naught becomes nearly R T and H T naught becomes nearly H T. Until that time, we run this model and then finally obtain the solution. So, that is the procedure. Then what we do? Let us say that we started with a value of P, say 0.65. That means, we say that 65% of the time the irrigation demands have to be met. Subject to that, we are looking at what is the maximum power that can be generated. So, we get one certain power that can be generated, that is the maximum power that can be generated corresponding to the irrigation reliability being 65%. then we increase the irrigation reliability from 65%, let us say I make it 70%. Then what happens to the power? Power has to reduce, because you are going to supply more water to irrigation, and therefore, the power has to reduce. The maximum power that can be generated corresponding to an increased level of reliability of meeting the irrigation demand will be lower. So, as you increase the reliability of irrigation, reliability of power will come down, and therefore, the maximum power that you can generate will be smaller. So, like this, we solve this problem again and again by each time increasing the reliability level until it becomes infeasible. Let us say that you keep on increasing the reliability, unless the problem is let us say that there is no limitation of water and there is adequate storage that is available. So, you may hit reliability of 100%, meeting the irrigation demand 100% of the time, and then you will get a maximum hydropower. But in general, what happens is, as you start increasing the reliability, you will hit a certain reliability level of irrigation release, beyond which the problem becomes infeasible. That means, you may not be able to increase the reliability of meeting the irrigation demands beyond a certain point, because the inflows are limiting or the storage is limiting, and at that point you stop. So, you have generated essentially for various levels of reliability of meeting the irrigation demand, you will generate the maximum hydropower that you can generate. The solutions provide you the maximum hydropower that you can generate corresponding to a given reliability of meeting the irrigation demands. That is what is the idea there. So, we will just look at some specific application. In fact, this is the Bhadra reservoir, and the details are available in this particular work, Srinivasan and Vedula. This is Sadhana, which is the Indian Academy of Sciences journal. You can just refer to this. But the idea here is to interpret the results. So, you have the total storage capacity 2024. In our notation, this will be KD, KT, I am sorry, and this is KD, and installed capacity is known. This I think we have used it as the variable BC, which is the installed capacity. So, we have this data BC, and inflow data of 52 years is used. Therefore, we know F of IT. I write this as FIT of IT, which means this is the CDF of IT. Is estimated from the historical data of 52 years. Now, each time a run is made for a particular value of P, and the corresponding inflow sequence for the 12 months will be used. That is what we are saying here is, this part you understand correctly, especially this is important for the new students who are not used to the concept of reliability and the associated flows here. So, this you understand correctly. We specify the value of P, which is the reliability of meeting the irrigation demands. Corresponding to this 1 minus P here, you will get the inflow here, and this is for time period T. Similarly, for different time periods, you will get different inflow value associated with this 1 minus P value. So, P is specified, let us say 65%, and therefore, this becomes 0.35. Corresponding to 0.35 in time period T, you will get one value. Time period T plus 1, you will get one value. Time period T plus 2, another value, like this, because you will have different CDFs associated with different time periods. And for the same value of P, you will get a different flow in different time periods, and therefore, for a given value of P, you will have a inflow sequence, and that is the sequence that you will use in your optimization. That is the idea here. Each time a run is made, run means run of the model is made for a particular value of P, the corresponding inflow sequence for the 12 months has to be used, and this corresponding inflow sequence for the 12 months will come from FIT of 1 minus P. P is fixed, FIT inverse of 1 minus P will give you that inflow value, and that is what we provide here. So, for month flow, this is for P is equal to 0.65 as an example I am showing, P is equal to 0.65. These are the inflows that we obtain. That means, essentially we would have fit a CDF. Now, in the absence of any rigorous methods, you simply use the Weibull formula to fit the CDF, that is arrange them in the decreasing order and then associated probabilities you calculated, etc. You please refer to the stochastic hydrology course, in which some rigorous methods are given for estimating the CDF for a given sequence of inflows. For this value of 0.65, these are the values which correspond to FIT inverse 1 minus P. So, these are the values. So, you get one sequence associated with a specified value of P, and these are the demand values which are specified, they are independent of the reliability, remember. Now, these are the irrigation demand values known. Alright. So, when we solve this, you get a certain maximum hydropower that is generated. Then you increase P, let us say P is equal to 0.65, you make it P is equal to 0.7. This inflow sequence will change. As you change this, the inflow sequence will change, because that will depend on the probability level, and for each of the month there is a different CDF, and corresponding to that particular probability level, in fact 1 minus probability of that, you will get a different inflow, and as you change P, the inflow sequence will be different. Therefore, you rerun the model, keeping the irrigation demands the same here, and then you will get another maximum value of power that is generated. Remember, every time that you solve the problem, you will get maximum EBT, that is sum of EBT, which is the total power that is generated over the year, and thus you will get a trade off between the reliability of meeting the demand P versus the maximum power that you can generate associated with that reliability of meeting power demand, and that is what we get here. So, here you will get the reliability level, you fixed 0.65, for the 0.65 it comes to somewhere around 6, this is billion kilowatt hour. So, the unit is kilowatt hour here and million kilowatt hours. Then as you increase reliability, this will be smaller and smaller, beyond a certain point you cannot increase further. So, you cannot go beyond, let us say 0.7, 0.8 and so on. You can examine that. If you increase the reliability further, the problem becomes infeasible, and therefore, you will start looking at how much can I increase the annual energy. If I want minimum of 30 million kilowatt hours, what is the reliability with which I can meet the irrigation demand. So, I may have to sacrifice the irrigation reliability to about 0.58, let us say, to achieve a minimum energy generation of million kilowatt hours, 30 million kilowatt hours. So, this figure that you are seeing now provides you a good tool with which to make decisions on how to operate the reservoir. Do I operate the reservoir at 55% reliability of meeting the irrigation demands, in which case I will get higher power, or do I sacrifice on power and meet the irrigation demand at a much higher level. Let us say I want to meet at 65%, then I will be able to generate only 5 million kilowatt hours. So, this gives you a trade off between irrigation, reliability and the power that can be generated. Associated with every solution here, remember there is a operating policy. What do I mean by operating policy? You will get the BT, which are the decision parameters, as the decision variables out of the optimization problem. The BTs in fact will decide on the operating policy, because ST plus 1 is equal to BT, and therefore, BT which comes as the decision variable will dictate the storage that is to be maintained at every time period, and that becomes the operating policy. So, the operating policy here will be decided based on a trade off between the reliability of meeting the irrigation demand here and the associated maximum hydropower that you can generate. Remember, this is the maximum hydropower that you can generate associated with this particular level. And how this gets decided? It gets decided because associated with this reliability level, there is a particular inflow sequence that you need to use, and that inflow sequence, which is governed by the probability distribution of the inflow, which has been determined based on the historical data, that will dictate how much power, how much water is available for power generation after meeting the irrigation demand at a particular reliability level. So, this is how you optimize the hydropower generated. This is one of the methods where we have used the chance constraint method. You can also use the stochastic dynamic programming, you can use the Bayesian stochastic dynamic programming and so on. So, there are several methods available for hydropower generation, hydropower optimization. This is one of the simpler way of doing it by considering the inflow uncertainty. Now, before I close the hydropower discussion, I will just explain how we do multi-reservoir operation for hydropower generation. Within just 1 or 2 minutes, I will just explain this. Now, this is the KHEP stage 2, that is Karnataka Hydropower project, hydropower project stage 2, where you have the Soper reservoir here and you have Nagsari powerhouse. There is a powerhouse here, there is a powerhouse here, and at Kadra there is a powerhouse here. Now, this is a multi-reservoir system operated only for power generation. I have discussed in the earlier lecture when I discussed hydropower how to simulate for single reservoir. Use the same procedure for multiple reservoirs, except that at every reservoir you look at the total contribution coming from upstream reservoirs. For example, this Upper Canary reservoir is a balancing reservoir which will supply water as and when it is required. Similarly, Tattihalla is a balancing reservoir, it will supply as and when it is required. Bommanhalli supplies to Nagsari powerhouse. So, the main powerhouse here is the Nagsari powerhouse. There is another powerhouse here on Supa dam. There is another powerhouse here at the Kadra. Suppose, for example, you are looking at the Nagsari powerhouse simulation. Then what you need to look at, you see all the intermediate catchment flow that comes here plus the release contribution from the Supa reservoir. Now, that release contribution comes out of the powerhouse, therefore, it would have generated certain powerhouse. So, look at the total power that is generated at Supa reservoir as well as at the Nagsari reservoir. At every reservoir, you just look at the continuity of that particular reservoir, how much is release that is going out, how much that has been coming from the intermediate catchment as well as from the upstream reservoir and so on. So, you have, for example, here you have Bommanhalli contributing here, something comes from the Nagsari powerhouse, and there is also an intermediate catchment flow that comes here, and that feeds into the Kadra reservoir. So, you write the continuity equations at each of these reservoirs by accounting for what is coming from outside upstream reservoirs plus what is coming from the intermediate catchment flow, and then generate the power using the same single reservoir power simulation, single reservoir simulation that we have studied earlier. So, typically then what you get in such a situation is the working tables. For example, for Supa reservoir, you will look at the working tables. Now, this working table is similar to what we had discussed earlier, except that here we have considered the multi-reservoir operation. So, we take into account the multi-reservoir operation and then simulate the hydropower at each of these locations. So, essentially then we have discussed in today's class the hydropower optimization, specifically dealing with the using the chance constraint linear programming for a single reservoir system, and then I have just explained towards the end of the class how we use the multi-reservoir simulation for hydropower generation. These are available as handouts. So, because the multi-reservoir simulation I could not cover in detail, but it is just the extension of what we do for single reservoir systems. Thank you for your attention. We will continue the discussion.